Okay, so in today's lecture, we will mainly focus on understanding vector spaces because it will be helpful not only in understanding group theory in the future time, but also differential geometry. So I plan to teach this in a more mathematical point of view. So we start with maps. So what do you mean by a map? So consider you have set of elements. So X is a set and Y is a set. So X contains a set of elements, say X1, X2, dot, 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 dot. And Y contains a set of elements, Y1, Y2, dot, dot, dot. Now, what a map does is it takes you from one element in X and drops you at another element in Y. Okay? In another way, if X is an element of capital X, so X is an element of the set capital X, then when the map acts on X, then the result that you get belongs to capital Y. We all know these things. Okay. Now the set X, so now some usual definition. So there is something called as domain. Now the domain is actually the set X here is the domain of map. So set X is domain of map F. Now what is the image? Now the image is the set F capital X. So why I'm writing F capital X? So you see when you go from capital X to capital Y, when the elements are going, you may not go from all the elements of X to all the elements of Y. Okay, maybe all the elements of X are mapped into only 2 elements of Y. It's a case. Maybe there is a mapping which maps all the elements of X to only 3 elements in Y. Okay, so all those elements to which the X is being mapped to, that is called the set F of X, or in other words, it is called as the image. So what F of X contain? So F of X is a set which is also called as the image. All the elements of F of X, of course, they belongs to Y, such that Y is equals to F of X for X belongs to capital X. So this is the condition, that the set F of X should contain all those elements Y on which you drop through the mapping. Okay. Let me give you a very small example. Consider F of X is equals to sine X. Then your F is a map that takes you from X. Now say X is R, all the real numbers, and it takes you to sine of X. And all the values of sine of X, they lie in some Y. Then you can see one thing, that the image of the map, so image of map whose domain is R, it does not take all the elements of Y, but it has all the elements of Y between -1 and 1. You see? So if Y is also R, then not all the elements are the image, only those elements are the image upon which you drop when you do the mapping. That's it. Then some ideas about homomorphism. And this is the word that I will use a lot while doing group theory and also differential geometry. So what is homomorphism? So consider a map again, F, which takes you from set X to set Y. Okay, but if this map is so special that F preserves the algebraic structure. What does it mean? What does it mean that X preserves the algebraic structure? For example, consider A and B, they belong to the set X. Okay, and when you multiply A and B, which is also an element, say it also belongs to X. That means you got A and B, which is an element, after multiplication of A and multiplication of B. Then homomorphism, what it does is, it says that, look, I am a special map such that if you calculate the image of element AB, which is f of AB, then this image is equals to, take the image of f of A and multiply it with the image of f of B. So homomorphism means all those maps which preserve the algebraic structure. Here, what is the algebraic structure? Here the algebraic structure is the product operation. So under product, you see that F turns out to be a homomorphism. Okay. Then if a homomorphism F is bijective, then F is called as an isomorphism. So if F is bijective, then homomorphism F can be given another special name as isomorphism. Okay, so we can say that if F is an isomorphism, then we say that the elements of X are isomorphic to elements of Y. So what is bijective? It is both 1, 1 and on 2. Okay, so these are some things that you can easily find out. So why I taught you this is, now whenever I teach something from now on, I want you to think only in terms of maps and functions. Okay, that's the main idea. Okay, so what I'll tell you now is, I'll tell you about say vector space. So what is vector space? So vector space is nothing but it is also a set. So vector space is also a set like any other set, but it is not just like any other set. It has certain property that it needs to be satisfied. So for example, the vector space says, look, I am a set such that if you take two elements within me, so if this belongs to vector space V, then V plus W can be found in V. So the set is a special set where if you take two elements, you add them, the element exists in V. Okay, just like in the group, there was, if you take two elements in the group and you multiply them, if the operation is multiplication, so if you multiply them, it exists in the group, which is a closure property. Same here, it happens with the addition property. Then it also says that if you take any element V which belongs to the vector space V, then multiply any scalar C with V such that C scalar is belongs to R, set of real numbers, then C of V also belongs to the vector space V. Okay, that's it. So these are the main two properties that the vector space satisfies. So if a set satisfies this property, these properties, then you can call it as a vector space. So whenever I use the word vector space, remember it's a set with certain property. Whenever I use the word group, you always think of a group as a set of elements with some property. Okay, so you think in that way and remember the properties. Now in vector space, there is something very interesting about inner product. You might have heard about this. Now inner product is another algebraic another property that you can define in vector spaces. So the inner product says that if you take two elements, so V and W belongs to V, then if there exists an inner product which is represented as like this, if here is a V and here is W, then the inner product, when you do it, you should get a value in R. That's it. You should get a value in R. That is inner product. For example, remember length. So when you calculate length of a vector, what you do? You take a vector and do inner product or dot product with itself, and you get just a number. So dot product has another name, which is inner product. So whenever you take inner product of two vectors, then it means that you are going to get a number. And the set is very special. When I say vector space, it is saying that you have a collection of vectors. Okay, so now I'm going to put arrow signs here to tell you that now we are dealing with a set that contains only vectors, and the set satisfies certain property that we saw just above. Okay. Now the inner product can be defined as a map. This is what I wanted to teach you. So whenever you think of inner product from now on, you should think of an inner product as a map. Let us see how. So the definition of the inner product is such that it is a bilinear form. It is a bilinear form on the vector space V. So basically, when I say bilinear form, I'm talking about that the fact that inner product is a map, and let me represent the map as like this and a comma and like this. So you can put an element here and you can put an element here. So I'm removing the element, I'm just putting the bracket and the comma. So inner product is a map that takes two values from the vector space, or takes two elements from the vector space, and it maps them to R. That's it. That's the definition of inner product. Okay. Now the inner product is actually linear in coordinates. So the interesting thing about inner product is it is linear. What do you mean by that, linear? It means that if you take a vector u plus v this side, put a comma and take another vector w here, and you do this inner product, then you can see that things turn out to be very simple. This and this plus v and w. Okay. So there are some more properties of inner product. First of all, the inner product is symmetric. By symmetric, I mean that if you take the inner product of v and w, then this should be equal to the inner product of w and v. This is called symmetric property. Similarly, the second one, it should be positive definite. So positive definite says that if you take v and the same element and find the inner product, then it should be always greater than 0 for all v belongs to the vector space V. So all vector V belongs to vector space V. This is the condition. That's it. Now, does all vector space has this property? May not be. But if the vector space for a vector, if a vector space is equipped with inner product, we call it as an inner product space. So let me write it. So if you have a vector space which is equipped with inner product, then such kind of vector space will be called as inner product space. That's it. Okay. Now remember we talked about a basis. Okay. So every vector product contains basis. Oh, sorry, every vector space contains basis. Remember I talked about a vector space R2 and I said that it has two bases, 1, 0 and 0, 1. And any element of R2, say 3, 4, can be written as a linear combination of the bases. Now these 3 and 4, they have a very interesting name. They are called as coordinates. Okay, the 3 and 4 is called as coordinate. Now a vector space that has a basis, it means that any element of the vector space can be written in terms of a linear combination of bases. So now there is an interesting thing. When you are in R2, there are two bases. When you are R3, that is in three-dimensional space where every point is a vector. In R3, there were three bases, as I said, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So it turns out that if you are in R2, you need two bases. If you are in R3, you need three bases. So similarly, if you're working with Rn, by Rn you are in an n-dimensional space where every point is represented with n numbers, x1, x2, dot, 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 etc. Just like if you are on a flat plane, each point is represented by two numbers using the origin. If you are in 3D space, to represent each point you need three numbers. Similarly, in n-dimensional space, to represent each point you need n numbers. And for every point you can always draw a vector. That's why these points are also called as vectors. And for Rn, there will be n bases. Okay, so how, and the basis will be n dimensional. So there will be 1, 0, 0, dot, 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 n times. Then there is 0, 1, dot, 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 n times, n times, n times, and there will be 0, 0, 1, dot, 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 n times, and so on. There will be n such basis vectors. And now any vector in the vector space Rn can be written as a linear combination of the bases. Okay. Now this I want to represent in a mathematical way. Okay. So I do it in the following way. So how do I do it? So consider there is a vector space X, and I would represent all the elements of vector space X by such a symbol. So when I do this, always remember I'm actually doing this. I'm writing all the elements x1, x2, x3, dot, 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 dot. If I say that UI is basis of X, and say X is R2, for example. Okay, say X is R2, for example. Then if I write this is the basis, then you should immediately recognize that the basis contains two elements, U1 and U2. Since we are in R2, and any element of X can be written as a linear combination of u1 and u2. Similarly, if I'm in n dimension, that means if X is nothing but Rn, then I would indicate that my basis ui like this. So this is the basis. So whenever I write like this, you should be careful. First, you should remember whose basis am I writing. Since I'm writing the basis of Rn, you should know that there will be n basis, and any element that belongs to Rn can be written as a linear combination of all these bases. There is a shortcut way of writing this. So I write x1 is equals to summation I 1 to 2 so xi is a I j u j, and here xi is summation I equals 1 to n a I j u j. Okay, so this is a shortcut way of writing, and let's try to understand this shortcut way of writing this. So focus on R2. What did I write? I write that any element is written as summation I goes from 1 to 2 a1 j uj. That means consider for I equals to 1, you have the first element of x. Then there will be summation. So I'm using Einstein summation convention, so I'm removing the summation. So it will become ai j uj, and j is going from where to where? Oh, sorry, here I should write j. Here I should write j, and here I should write j. Yes. So j is going from where to where? In R2 it goes from 1 to 2. So you'll have a1 1 u1 plus a1 2 u2. Similarly, for I equals to 2, you should look at the second element, and the second element will be a2j uj. That turns out to be a21 u1 plus a22 u2. So as you can see, the coefficients are different for different elements. Okay, this is the beauty of this simplified representation. That's it. That's the main idea. So what I will do is I will mostly work in R2 for simplification, and you should always go to Rn for complicated stuff. So in every book they always work with Rn. We will do only with R2 as far as possible. Okay, for simplicity. Now let us discuss something about change of basis. Change of basis. Well, the idea that you are changing the basis tells you that given vector space, the basis that you choose is not unique. For example, in R2, if you choose the vector space to be 1 0 and 0 1, then you can write element 3 4 in terms of this basis 1 0 and 0 1. Now I want to tell you something. Remember, I said that I made arrow here and here, and I said these are called as coordinates. Although they coincide with this 3 and 4 here, but I didn't call this 3 and 4 as coordinate. I called the number that exists here as the coordinate. Why I did it? We'll come to that right now. As I said that the basis is not unique, you can choose another basis. For example, another basis is in R2 can be 1 2 and 1 3. Okay, so just remember this can also be written as 1 0 and 0 1. This is just the style of our notation. So if you look at this, then consider any vector v. So consider, let me name it. Let these bases be v1 and v2 in R2. Then if you have any vector v and let the vector v is 1 7, then in this basis v vector can be written as 4 v1 minus v2. Now you see these are the coordinates of v in the basis 1 2 and 1 3. So let me call this basis as basis b. So the coordinates of vector v in the basis b is equal to 4 and minus 1. Now you would say that, okay, these are the coordinates, then what are these? Well, 1 and 7 are also coordinates, but they are coordinate in the standard basis. So this basis 1 0 and 0 1 has a name. It is called as a standard basis. So this is 1. As I said, I can choose one more basis. So let's work with R2. And what is our vector in R2? We choose the vector to be 1 7. Now I choose another basis. Let that basis be 3 1 and 2 1. Well, they form the basis because they are linearly independent. I'll not explain that. It's very simple. So I'm just giving you a basic idea. So I can now write vector v is equals to, so let this is be basis v1 and this is be basis v2. Then I can write here v turns out to be minus v1 vector plus 4 v2 vector. That means the coordinates of vector v, which is 1 7, in the basis c turns out to be minus 1 and 4. So the coefficients that appear before the basis, they are called as the coordinates. Now let me give you one more example of a vector space to just make you think a little bit bigger and in a broader sense. Well, consider you have a vector space V, and this is not the vector space of R2, which contains numbers, but consider this is a vector space of functions. So consider this is a vector space of functions. Now, since this is a vector space of functions, that means let me choose a basis B is 1, x, and x squared. That means any element V, which is an element of vector space V, can be written as a linear combination of the basis gamma x squared. Okay, so for example, if I write an element, so I should remove the vector now. It's bad to write vector. So let me represent it as V. So let V, or let me use P. So P is a polynomial, and say it is of this form, 5 plus 7x minus 3x squared. Then can you tell me in the above basis B, what are the coordinates? It's very simple. The coordinates are 5, 7, minus 3. Okay, because it is written in the form of basis. You can find alpha, beta, and gamma. But I said bases are not unique. So the space of function can also take into consideration another basis, and let it be 1 plus x, the first basis, comma 2 plus 3x, second one, comma 5 plus x square, the third one. Now I ask you, what is P in terms of this basis. How you calculate? So multiply C1 with the first basis, multiply C2 with the second one, and multiply C3 with the third one. And you know already what P is. Equate, find the coordinate C1, C2, C3. So now the function P in coordinate C, in basis C, will have the following coordinate: 40, minus 10, minus 3. It's a simple calculation that you can do. So the fundamental idea is that every vector space do not have a unique basis. It depends on your choice what basis you are using. That means if you can change the basis, that means if you are going from one basis to another basis, that means you can find, you can talk about change of basis using some matrix. Okay, so consider now, let me write in a general way. Okay, so consider that you have a vector space X, and the first set of bases in the vector space X were U, J. So if you are in R2, so let's always be in R2, then your basis is U1, U2, and now you change the basis. Now you want to work with another set of bases, and that's why I put a prime here, and I can put I, J, whatever I want. So in R2, you have now changed your basis. You are working with a different set of basis, and we know what does it mean. That means you can talk about the following thing. You can say that, okay, I moved to a new basis by using certain transformation 1 to 2 A I J U J. That's it. So you went from the old basis. So this was the old basis. Say the old basis was 1, 0 and 0, 1, and the new basis was taken to be 1, 2 and 1, 3. Then you can always find the set of matrix A I J that transforms or takes you from one basis set to another basis set. Okay, now usually when you have a matrix, so consider you have a matrix A, and you know that the matrix A has elements, say A11, A12, A13, and here A21, A22, and dot 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 dot, so many. Then in some book they write this matrix in this way. So they will do just Aij like this. So whenever you see this notation, you know that they are representing a matrix with elements Aij. Okay, so this is the fundamental idea behind change of basis. So you can always find a matrix if you are in R2, R3 or Rn. If you are in R2, you will always find a 2 cross 2 matrix that takes you from one basis set to another basis set. Okay, quite easy. Okay, let's try to find the matrix in this case. Okay, let's do an example for convenience. So what is our old basis? Our old basis is 1, 0 and 0, 1, and our new basis is what was it? 1, 2 and 1, 3. 1, 2 and 1, 3. Okay, so how can you find a transformation? So you know that the new basis must be some 2 cross 2 matrix. So let me write A11, A12, A21, A22 multiplied with this, and all we need to find are these values A11, A22, just multiply. So a first multiplication gives you A11 and the second multiplication gives you A21. I hope I'm correct. Yes. So that means from here you found A11 turns out to be 1 and A21 turns out to be 2. Now work with the second one. So you have 1, 3 and you again have A11, A12, A21, A22 and this time 0, 1. I hope I'm doing it correctly. Then in this case, what do you get? A12, A22. Okay, so am I correct? A12, A22. So it turns out that A12 is 1 and A22 is 3. So did we just find the matrix? A11 is 1, A21 is 2, A12 is 1 and 3. So this is the matrix A that takes you from one set of basis to another. Here you got a very trivial example because you were going from the standard basis to another basis. But if you would have gone from a basis like, say you are going from 1, 2 and 1, 3, and you are going to a basis like 2, 1 and 2, 3, then you'll get a non-trivial matrix. So this is the whole idea behind change of basis. All I want you to right now remember just one thing, that in n dimension the notation of change of basis is the new basis ui prime can be represented as j1 to n. So aij now turns out to be n cross n matrix and the old basis here. So now you have a n cross n matrix that is making your transformation of basis. Okay. Now there is a very interesting thing that we can do is how if the basis is transformed, then you can always find a matrix that takes you from one coordinate or one vector element to another element. That is, what I want to say here is, we did some examples, right? Let me put up the examples. So you have your V, which was 1, 7. When you used the basis 3, 1, when you used the basis 1, 2 and 1, 3, and I call this B, then the coordinates of the vector V in the basis B turned out to be 4 and -1. The same vector, when I used a different set of bases, the same vector in the basis C and in R2, we found that the coordinates of the vector in basis C turns out to be -1 and 4. That means if there is a matrix that takes you from the B basis to C basis, so if there is a matrix that transforms the basis B to basis C, then there should be a matrix that will help you transform these coordinates to this coordinate. And we know that these two matrices must be somehow related. I mean, the matrix that transforms the coordinates should be somehow related to the matrix that transform the basis, because when you change the basis, the coordinates of the vector also changes depending on the basis. Okay, so let me write a notation for this. So the notation that I'm going to use is the following. So when you have a transformation of basis, so when you go to the new basis by using 1 to n, so I'm writing n if you are in Rn, ij and uj, then this change of basis will cause a change of coordinates. So I want to write it like this. So somehow the old coordinate will be related to the new coordinate by some matrix, say b j I x j prime, the new one, and there will be summation over, I made a mistake. Okay, let's do one thing. Let's ease up the notation. Yeah. So when your basis change in this way, then I want to say that there is a matrix where using which you can go from one coordinate to another. So let's go from old coordinate and use a matrix b j I with the new coordinate here. That's it. So whenever there is a matrix that changes the basis, of course there will be a matrix that changes the coordinate. But I said there should be a very deep relation between these two matrices. They should be somehow interconnected. May not be equal, but they should be interconnected. So the idea is, if we know the matrix that changes the basis, is there a way we can calculate the matrix that changes the coordinates? That we will do in the next lecture now. So it's very simple. It's a very simple derivation. So the idea is, if you know matrix that transforms basis, then can we find matrix that transforms the coordinates? Okay, let us start. So consider we know this relation, that is summation j goes from 1 to n a I j u j. Well, I want to use a shorthand notation. I'm going to use Einstein summation convention. Whenever a indices is repeated, no, there is a summation. So I'm going to use this. Okay, so consider you have a vector x, okay, and the vector x, when written in the old coordinate, it can be written in this way: xi u I. Agreed? This is how I can write the x. But now I know, and also x, if I write the vector x in the new coordinate, then I should write something like this: xi prime, because the coordinates will also change, ui prime. Okay, you know that every vector can be written in terms of basis, and the coefficients are called coordinate. If it's a different basis, your coordinates are different. Okay, so let us start with this. So I took a vector x which belongs to the vector space, capital X, and I wrote it in terms of one set of bases ui, which I know. Now I know that this though remains xi, my this is say xi prime. Okay, and what is ui prime? Ui prime is aij uj. Why I equated them? Because we are talking about the same vector, right? It doesn't matter in which basis you have written, we are basically talking about the same vector. That's why I can equate this and this, which means basically I have first equated xi ui to xi prime ui prime, and then I substituted ui prime from here. Okay, very simple. So let me write it. So I have xi ui turns out to be xi prime aij uj. Now in both sides uj are linearly independent, right? These u's, they are linearly independent. U's are linearly independent. So what does it mean? If u are linearly independent, then we can just equate the coefficients. So I can write xi equals, or I can write it in another way. So I should write xj, more specifically xj equals xi prime a I j. Okay, now this can be written in a different way. This can be written as a j I xi prime. Now you would ask me what a j I is. So let me write in this way. So a j I is nothing but it is a transpose of aij. Okay, so whenever you transpose a matrix, the coefficients interchange. I hope you know this. For example, you have a11, a12, a21, a22, and if you transpose it, then what happens? In place of a11 there is a11, but in place of a21 there is a12, in place of 12 there is 21, and this stays same. That means if this is a matrix aij, then this should be aji, and they are related by a transpose. It's quite simple. That means the matrix that transform the basis, that transform the old basis to the new, the transpose of the matrix is the matrix that transforms the coordinates. In short, the matrix, so this is your, what does it mean? When I write this, it means you are going from old to new, and the matrix that takes you from old to new, its transpose takes you from the new coordinate to the old coordinate. That's it. So the moment you know the change of basis matrix, you can easily find the matrix that transforms the coordinate. Okay, you can take it as an exercise, and you can calculate these things based on what examples I have given. Okay, so what you can do is, you know, there were two bases, 1 2 and 1 3. Find a matrix that transform this basis to okay, so this is 3 1 and say 2 1. Okay, so make it a fine matrix, transforms the basis, and then you can easily find, if you know the coordinate here, the coordinate here was 4 minus 1, then you know that using this idea, using this matrix, you can easily calculate what are the coordinates in the new basis, which I think turned out to be minus 1, 4. Please give a check here. Maybe I might be a little bit confused with the basis, but give a quick check here if I'm correct or not. Okay, so the idea is clear, right? Any doubts till now?
No.
When you transform from one basis to old basis to new,
Another basis.
yeah. So in the old basis, the
Of course,
dimensions of old basis and dimensions of new basis should be same, right?
Yes, you are in R2. You are always in R2.
So can we transform from means one dimensions to another dimensions?
In that case, you will get what kind of matrix? You'll get rectangular matrix,
Yeah,
not a square matrix.
not a square matrix.
It is possible. Maybe I'll give you an example
Okay.
after this.
Okay.
Okay, let's end it.